All right, this is the second hour of Physics 1b for whatever today is, November 22nd. Okay, so what did you all figure out? I asked you all to look at this function right here, y of x comma 0. That's why there's no t in here, so it's really just a function of x. And we said that a times the cosine of 2 pi x, for what values of x does this quantity equal a? What did you all figure out? There's more than one answer. Anyone there? Were you not able to figure it out? It works for whole numbers, like 1, 2, 3, etc. Okay. Do other people agree, or? You thought it could work for any x. You're telling me any value of x you put in there, it worked, Mary. Did you try it in a calculator, or did you just... Where'd you come to that realization? So if we try x equal to 0.5, I know for a fact it's not going to work. If we try x equal to pi, how about that? You said any value of x. What if we do y of x equal to a times the cosine of 2 pi? What if we put in pi here? Is that going to work? Was this too confusing as to what I asked you to do? Do I need to be really specific? I don't understand. Astral lever is correct. That is the right answer. It's not any value of x. If you take your calculator, right, make sure your calculator's on radian mode, and you plug in cosine of 2 pi, and you multiply by, you think x needs to be an even number. I don't think it has to be even, but we can check. So if we put cosine, so yeah, if you do this, this isn't going to work. That's just stupid. We know cosine of 2 pi is equal to 1, right? And when you throw an x in here, where x can be any value, right? Remember, it can be any value. It can be half, it could be e, it could be 1.75, it could be anything. Then the only values of x that are going to satisfy this equation are going to be the values of x that make it so that this is still equal to a whole number multiple of 2 pi, right? So if we plug in x equal to 1, right? So if we do y of 1, you get a cosine of 2 pi, and that's equal to a. If you do y of 2, I left out 0, but 0 works as well, right? You can do 0 as well. Then you get a times the cosine of 4 pi, and that's equal to a. If you do y of 3, then you do a cosine of 6 pi, and that's also equal to a. You can plug these into your calculator. Cosine of 2 pi, cosine of 4 pi, cosine of 6 pi, you'll get 1 for all of those, right? So the thing about this equation is that it's not very good because it's the values of x that satisfies this equation are only 0, 1, 2, 3, etc. And these would have units, right? This would be 2 meters, 3 meters, 1 meter, etc. So that's not really going to work because we want our function, what is our goal here? We want this function to repeat itself every x equal to lambda and t equal to t, right? So in order to make that work, right, when x is equal to lambda, we need to divide this by lambda, okay? So if I put into this equation here, let me erase this. If I put into this equation here 2 pi over lambda, now, for what values of x is, we can ask the exact same question. For y of x equal to 0 equal to a, for what x is that true, right? For what values of x is y of x and 0 equal to a? Now, instead of being 0, 1, 2, 3, think about it for yourself for a second. What values of x will make this equal to a? If I put 2 pi divided by lambda times x, now what values of x will work? Obviously x equal to 0. That's still going to work, right? Because I put x equal to 0 in here. Yeah, the whole thing will be 0. Cosine of 0 is 1, right? What's the next value for which you, because these are it's a periodic function, right? What's the at x equal to 0, you get this works. What's the next value of x that will give you, basically, what's the next value of x that will make this equal to 2 pi? I want that whole thing to be equal to 2 pi. What does x need to be equal to? Lambda. And then if I want the whole thing to be equal to 4 pi, what would x need to be equal to? Because 4 pi is the next time it's going to be equal to 0, right? What's the next value going to be if I want this whole thing to be equal to 4 pi? 2 lambda, right? So now my function is going to repeat itself in terms of its shape every lambda. And what's lambda? Lambda is the wavelength, right? It's the distance between this point and this point, right? So if this is lambda, right, I want it to repeat itself every lambda, right? It'd be better to see down here. Well, yeah, because we want this point and this point to be the same as each other, okay? So we now know what the value of, well, the shape of our function is. It's going to be something like this. So now what we need to do is we need to take this equation here and this equation here, right? And we need to link them up together somehow, right? You have to find some way that we can link them up together, all right? So how can we do that? Well, what we can notice is that if we look at, which one's the best one to look at? So we know that the wave travels with a velocity that's equal to lambda multiplied by the frequency. And we also know that if we were to compare 2 points of our wave, let's say that we compared, I don't know, like, I guess this point here and this point here. The connection between the two of them is going to be that we have this repetition occurring, and they're separated in space and they're separated in time. And the repetition in time is going to occur something like, how do you actually, what's the best way to put these together? How do we combine together this equation and this equation? I mean, I know what it's supposed to look like, but I'm trying to think of a logical way that we can take this equation here and this equation here and connect them together, put them into one thing. So I guess what we could do is we could say something like, the units of each of these, there's no units, because x has units of meters and this has units of meters, t has units of seconds, omega has units of 1 over seconds. So if we want to write them together in a function, we know we can add them. Normally the way this is written is like this. But I'm trying to come up with a way that I can explain to you why it is that we put them together like this. We know that by using the time dependence, that if we multiply by omega, that this thing will repeat itself every t, okay? Because omega is equal to 2 pi over t, right? This equation is the same thing as writing a cosine of 2 pi over t multiplied by t. So that hopefully you can see the connection between that equation and this one down here, right? So 2 pi over t times t, 2 pi over lambda times x. Maybe it, yeah. So how do we actually get them together? What do y'all think? Any ideas? How do we combine them together? We know what the spatial dependence should look like. It should look like this. We know what the time dependence should look like. It should look like this. How do we combine them together? What kind of argument can we make if we know that this wave travels with a speed v? How can we get down finally to this kind of result? What do we have to do? Would you all agree it's definitely not obvious? Would you all at least agree that it's definitely not obvious how we combine these two together to get this final equation down here? Would you all agree with that statement? It's kind of tricky, right? Okay. It's not obvious at all. So what we have to think about is like, how are these points on this moving wave connected to each other? And you have to kind of think about these two different variables, which we're not really used to thinking about functions of two variables, right? Normally functions you think about in your math class, you have like a y of x or a y of t, or maybe in your physics 1A class you had velocity as a function of time, position as a function of time. But these two extra variables here I think make this hard to think about, because we think of time as something that moves, and we don't think of it as something that's just a variable. Okay, so I'll tell you what the book says, and you can tell me if this makes any sense to you. So what they say is basically that the wave travels from some point x equals 0, from some point x to the right of the origin in an amount of time given by x over v, okay? So a point on the wave, I'm probably going to run out of space right here, so I probably have to go down a little bit. So a point on the wave travels from x equal to 0 to some point that is to some point x, to the right of the origin, in an amount of time, and this part I'll let you try to figure out yourself, equal to... Okay, so a point on the wave travels from x equal to 0, like right here, to some other point. Actually, it's probably better to like look at this point right here. Let's say that this was x equal to 0, just for shits and giggles. This travels to some new point, like let's say this point down here, right? So it starts here, and it travels to here. The string, right? The string doesn't actually move, but the point on the wave, the pulse of the wave does travel some distance. And it does so to get to that point x in an amount of time equal to what? How much time does it take for that point x to go from here to here if we know that the velocity of the wave is v? You can think about this just as like normal physics 1A stuff. I have an object, my wave. Here's my wave, right? What is the wave doing? The wave's moving. The wave moves with the speed velocity v, right? So if we call this point x equal to 0, and I call that point x, so it's moved a distance x, right? So we moved a total distance that's x. How much time does it take? What do I need to divide by here to get the time? Let me draw it in a completely different way. So take these 2 points. Here, let me put some string lines on here. So take these 2 points. This point here. Make it as straight as I can. And we take this point here, x over lambda ft. Okay, yeah, that's the right answer. Let me go ahead and draw this on here just to make sure that everybody understands that this isn't that complicated, but your book loves to make things complicated. If this wave, right, okay, if my wave is traveling at a speed, I'm going to ask it in a different way that I think will be easier to understand. So if I call this distance here delta x, okay? Sorry, that's kind of hard to read. It won't let me undo right now. Just erase it. If I call that distance right there delta x, your answer's right, Matthew. How long is that distance if the velocity of the wave is v? How long is this distance? It would just be velocity times what? Time, right? Yeah. So what's the time? So if a point on the wave travels from x equal to 0 to some point x to the right of the origin in an amount of time equal to t equal to x over v, right? You basically just move the v to this side right here, right? And now in this case, because we're choosing x equal to 0, that's why the delta x just becomes x, right? T equal to x over v, right? So what that means is that the motion of the point at x equal to 0 is going to be the same. Wait, how do they say this? So the motion of point x at time t is the same as the motion of point x equal to 0 at the earlier time t minus x over v. So the motion of the point x at time t is the same as the motion... Okay, nothing's getting cut off. The same as the motion of the point x at time t is the same as the motion of the point x equal to 0 at time t minus x over v. So this is the claim. I'm kind of trying to go through this like exactly as your book says it, because in other textbooks this is explained in a different way, and the last time I taught this class, what I did was I just used a different derivation that I thought made more sense. This derivation doesn't make sense to me, and so I know that not all of you, but some of you will actually read the textbook. I wanted to actually try to go through their derivation, and that's why I'm kind of going through this so slowly, is because to me the way that they talk about this doesn't make a lot of sense, and so I want to make sure that we can talk about it together, understand what it means, and then try to go from there, right? Okay, so a point on the wave travels from x equal to 0 to some point x to the right of the origin in an amount of time t equal to x over v. I think that's pretty understandable. Does everyone understand that part? To get from the point 0 to x, the time taken is the distance that you would travel divided by the wave. That's obvious, right? The next part is the part about that I think is kind of confusing. It says, so the motion of the point x. So now we're not just thinking about, we're just looking at some point x, some random point here, right? The motion of that point at time t, where now we can probably assume that time t is going to be related to this one, is the same as the motion of the point x equal to 0 at time t minus x over v. Okay, so we can find the displacement of a random point x by taking this equation here, right, and replacing t with this. Okay, so this is y of x equal to 0, right? So to find the motion of of a point at x, we replace t with t minus x over v. X over v. So this becomes y of x and t equal to a cosine of, what is it now going to be? Omega times t minus x over v. The idea would be that this is the motion of the point at x equal to 0, right? And this is the motion of a point at x equal to x. Motion of any point, you could say. We'll just say x equal to x, even though that kind of seems stupid, but... Does that line of logic make sense? Does that line of logic make sense? The point on the wave travels from x equals 0 to some point x. We got that part. We know this basically is just saying things travel at a speed v. The next thing we say is the motion of the point x at time t is the same as the motion of the point x equal to 0 at this time, because after all, if we shift in time by a time that's equal to x divided by v, we're now looking at another point that's moving with the exact same oscillation. And so that's kind of the argument. Does anyone have any questions? Did that make any sense to anyone? Yeah, it's interesting, but does it make sense? That's the question. The real question is, does it make sense? Going from this step to this step, I think is... I mean, all you're doing is replacing t, right? But the claim is that by replacing the t with this, you're kind of generalizing what point you're talking about, right? Because obviously this equation reduces back to that equation when we plug in x equal to 0, right? You put x equal to 0 in here and you basically get a cos omega t again. So that's good. The question is, does this part make sense, right? And the idea is that, you have to go through, like, each step here, but if it's true that the motion of the point x at time t is the same as the motion of the point x equal to 0 at time t minus x over v, which seems reasonable, right? Because the point x would move, at some point 0 moves to this point, which is this position, at this time, sorry. Anyway, I don't know if it's just because it's really early, but I've read through this derivation at least, like, I went through it last year when I was prepping for class, and it didn't make sense to me. I went through it this morning when I was prepping for class, and it didn't make sense to me. I'm still looking at this, and I'm thinking about it from the perspective of if I was a student, and I don't know that I would understand this, but so be it. This is how they describe it, and like, it does make sense to me to some extent, but I also just have a lot of questions about this. So if you do too, please feel free to ask. Anyway, whether you understand the derivation or not, if you aren't going to ask any questions, I guess we just go with it. I'm just going to assume that you do understand. The next thing we do is we take our equation here, y of x and t. Maybe this stuff just bothers me more than it bothers you. That's very reasonable. We know that, let's see, what's the next thing we can say? We know that the cosine of theta is equal to the cosine of negative theta, because they are, it's an even function. So we can rewrite this as omega times x over v minus t without changing anything. And then we can multiply through by omega. A cosine of this will become a cosine of omega divided by v times x minus omega t. And then we think about what omega divided by v is here. So omega, as I said before, was equal to 2 pi divided by frequency. No, 2 pi times frequency, excuse me. 2 pi multiplied by the frequency. And so if we say 2 pi frequency divided by v is equal to omega over v, it's the same thing. Then we look at f over v, and remember that v is equal to f lambda, so that f over v is equal to, what is it, 1 over lambda? Oh, that's going off screen. I'll scroll down a little bit. Yeah, f over v would be equal to 1 over lambda. So this would become 2 pi divided by lambda is the same thing as omega divided by v. This is what we came up with when we just kind of thought about things. So then we end up getting a cosine of 2 pi divided by lambda minus omega t. But we actually define this 2 pi over lambda to be equal to something we call k. We call this the wave number. It's just the inverse of the wavelength multiplied by 2 pi. And if we do that, we get our kind of final form here, which is the cosine of kx minus omega t. And that is our traveling wave. Traveling, it's a transverse sinusoidal traveling wave is what that describes. So it's transverse because the motion of the medium is up and down, perpendicular to the wave motion. It's sinusoidal because it follows either a cosine or a sine function. And it's traveling. We're going to talk about why it's traveling here in a second. Wave. That is our transverse sinusoidal traveling wave right there, that equation. Now I went through, let's go back to this beginning of this. So remember how we got here. We basically said that the motion in terms of time has to go as omega t the motion in space, we knew had to have this function 2 pi over lambda times x. And now we get that equation there. And this will repeat itself every one period and every wavelength as we want it to. Anyone have any questions? Oh, this is a transverse sinusoidal traveling wave in positive direction, x direction. If I wanted to get it to travel in the other direction, anyone have any idea how you do that? Oops. So we said that this was true, that t could go to t minus x over v. If we replace the velocity here with a negative number, then this would become a plus, this would become a plus, all the way down plus. So if I want to make the wave travel in the other direction, you have to do, as you guys are saying correctly, kx plus omega t. So y of x comma t equal to a cos of kx plus omega t. This one goes in the negative x direction. So this we'll just put down here. This is velocity in negative x direction. So it travels to the left, you could say. Oops. Now, the next thing to do, because I feel like these kind of equations like this are a little bit something we're not really used to dealing with. Like, you may look at this and you say, oh, there's a cosine. I'm comfortable with cosines. Maybe you spent a lot of time thinking about that, or you see the amplitude that shows up in front, and so maybe you're comfortable with that. But the fact that it's a function of x and t, I think, is what makes this so hard to visualize. So what I'm going to do, and the claim is that this motion here that we're seeing is described by that traveling wave, right? So I want to pull something up here on, you could do this on any type of graphing software that you want to. I'm just going to use Wolfram Alpha because I find it's just something I know how to use. But you could use Desmos or anything you want to show this. So what we're going to do is we're going to take our traveling wave function here, a cosine of kx plus omega t, and we are going to see what that looks like. We're gonna plot it basically, right? And I want to acknowledge that plotting this, you cannot plot this on like just two-dimensional graph paper, right? And plotting it in 3 dimensions may even be somewhat misleading because this isn't a spatial dimension, right? So we can't plot this like a 3-dimensional, like if you're taking Calc 3, for example. This can't just be a 3-dimensional function. It's a little bit different than that. So just to show you what I mean by that, we're going to plot the waveform. So it looks like a cosine of kx times omega t. I'm going to make a equal to 2. So times, we'll have a cosine of, I guess it's okay if we make k and omega equal to 1, right? Yeah, let's not do that. Let's make k equal to 3. So we'll have 3x minus, and we'll make omega equal to 0.5 or something. And now in here, I'm going to put in the time. But the first time that I'm going to plot is going to be t equal to 0, just to show you what this looks like real quick. That should work. I don't know if it will or not, but we'll see. Okay, so not surprisingly, when I plot 2 cosine of 3x minus 0, you get a cosine function, right? Normal cosine function. At y equal to 0, it's at maximum, and so on and so forth. So how can I visualize a traveling wave? Well, I'm going to have to look at what the wave looks like a few seconds later, right? So let's say that I look at what the wave looks like at t equal to 1 second. What is going to happen when I put in 1 second here? Is the wave going to move? Is this peak here going to go to the right, or is it going to go to the left? What do you think? We said that this was the equation for a traveling wave moving to the right, so shouldn't it go to the right? Shouldn't this peak here kind of shift off to the right somewhere, maybe? Okay, let's see. So let's click the equal button. Now, it may not be super obvious, but it does look like it's moved a little bit, right? It moved a little bit to the right. Now, Maybe it moved really far, and it just looks like it moved that distance, but it seems reasonable. The period is... The omega is 0.5, right? So what would the period be? The period is 2 pi divided by omega, right? So if we do 2 pi and we divide by 0.5, we get 4 pi, right? So the period of this wave is 4 pi. Okay, now if I plug in 2 here, of course, it's also going to move to the right again, right? And there it is. So that's the way in which you can kind of visualize this. You just kind of have to keep putting in individual numbers here, and you will see it move. Oh, it looks like at about 3, it's moved almost a quarter of a period now. Okay, so can we visualize all this stuff at the same time? Well, we can. So what we can do is we can plot all these functions simultaneously. So what I'm going to do is I'm going to just... Can't remember if I need to do anything other than just put commas in here. I think I can just put commas in here, though. I think it'll work just fine. So let's plot the wave at 3 different times all in the same graph. So at t equal to 0, t equal to 1, t equal to 2, t equal to 3. And what we'll see is a bunch of waves overlapping each other. It may be kind of noisy. No, it's pretty good. So here we have the wave. I like the colors. That's nice. So you can see even what the functions are too, right? So that's the wave at t equal to 0. That's the wave at t equal to... it's kind of hard to see because it's 0.5 multiplied by 1, right? So this is t equal to 1, t equal to 2, t equal to 3, and so on and so forth. And you can see it down here. This looks really nice. This nice little ribbony looking sine graph. So that's... Are you convinced? When I look at the equation and I look at this derivation here, I'm not convinced. For me, I'm very... I want to see what does it look like on a plot. So this convinces me that this actually works. You know, it's a traveling wave and it travels to the right. And of course, we can do one other thing here too. If I come in here and I put a plus sign in, it should basically be exactly what we see below, except, at least if what we said is true, it should travel the other direction. So if we do that, it's struggling. I probably messed up something in my... It could just be my internet sucks. Here we go. Equals. And there we go. It's going the other way now, right? Okay. Does that help you all to understand how this wave function thing works? I think we can do a problem now. Right? Yeah, waves on a clothesline. Okay, so we've got our traveling wave equation. We want to use that to solve this problem here. So this says, cousin Throckmorton holds one end of the clothesline taut and wiggles it up and down sinusoidally with a frequency of 2 Hz and an amplitude of 0.075 meters. The wave speed on the clothesline is v equal to 12 meters per second. At t equal to 0, Throcky's end has a maximum positive displacement and is instantaneously at rest. Assume that no wave bounces back from the far end. Find the wave amplitude A, the angular frequency omega, the period t, the wavelength lambda, the wave number k. Write a wave function describing the wave. Write equations for the displacement as a function of time of Throcky's end of the clothesline and of a point 3 meters from that end. There's a lot of things in this problem, but none of them are very challenging, actually. Okay, so what we have is we've got a person, cousin Throckmorton, who shows up in all these problems, and he is sending a wave down a string, and it specifically says Throcky's end at t equals 0 has a maximum positive displacement as an instantaneously at rest. So he's starting with the clothesline starts up here, and he's sending a wave on a string, something like that. It's traveling down the string. God, that looks awful. I really should have drawn a line before I did that. It's fine, I guess. So there's his awful-looking wave. We get maximum positive displacement here at t equal. This is the t equal to 0 looking part of this. The amplitude is 0.075, so this is the amplitude. The height of the wave is the amplitude A, and we're being told that this is equal to 0.075 in the problem. 0.075 right there. It says the wave speed, the wave is moving in this direction with a velocity equal to 12 meters per second. And that's it. That's all we know. We know this. Oh, and we know the frequency at which he's moving this up and down. So he's moving this up and down with a frequency that is equal to 2 hertz. So we need at least one other piece of information. And now we need to solve for a bunch of different things. First thing says the amplitude A. Well, we already know what that is. It specifically says amplitude right here. The angular frequency omega. Okay, so if we have F, we can get omega is equal to 2 pi times F. So 2 pi multiplied by frequency. By the way, frequency is usually measured in hertz, and a hertz, 1 hertz, is equal to 1 inverse second, or sometimes written as cycles per second, but that's not necessary really because cycles isn't really a unit, so we usually just write it as 1 inverse second, named after, I think his first name is Heinrich, I could be wrong. Hertz was a scientist who was the first person to verify the existence of electromagnetic waves as predicted by Maxwell when he created basically the first radio circuit, where he transmitted a wave from one end of a room to another end of the room. He was able to transmit and receive the wave, and he was able to prove that the wave exhibited wave properties such as wave interference that we're going to learn about. And he also proved that the speed of the wave was the same as the speed of light, thereby proving that Maxwell was correct, that light is an electromagnetic wave. And so we call the unit for frequency hertz, and that's a unit that shows up all over the place. It's very interesting, though, that this unit is one of the simplest units in the sense that it's just an inverse second, but it comes up so frequently that it's quite nice to not just talk about inverse seconds or cycles per second, and just call it hertz. Anyway. Okay, so that's the angular frequency. It's going to be 2 times 2 pi, so that would be 4 pi radians per second. The units for this are radians per second. Okay, next we want to find the period t. To find the period t, you just take 1 over the frequency, so 1 divided by 2 hertz. The units for period are seconds, so this is going to be 0.5 seconds. That's what the period is. Okay. The wavelength lambda. To get the wavelength lambda, we know velocity is equal to lambda times frequency, so that means that lambda is equal to velocity divided by frequency. So that's going to be 12 meters per second divided by our frequency of 2 hertz. So that's equal to 6 meters. So that means the distance between here and here is 6 meters. That's really freaking long. 12 over 2 though, that's correct. Part next is the wave number k. To find the wave number k, you just do 2 pi divided by lambda. So this one's not going to be just a simple number. I mean, I guess we could write it in terms of pi. Kind of. This would be pi over 3, I guess. Just put 6 down here. This would be pi divided by 3. The units for k are radians per meter. Or just inverse meters. All right. Part B says to write a wave function describing the wave. This is kind of the easiest part because once we have all of these things, we can just plug them in. So for part B, y of x and t is equal to a. So a is 0.075 cosine. Now how do I know it's a cosine? Well, it says at t equal to 0, his end has a maximum positive displacement, which means this is going to work. I'll show you how that would change if we had different information in a second. Okay, so a cosine of, and then we put kx, so k is pi over 3 times x, put some parentheses in here, minus omega times t, and omega is 4 pi radians per second, so this is going to be 4 pi times the time, and that's it. Anyone have any questions? By the way, this is the y direction. This is the x direction. Okay. Next, it wants us to write equations for the displacement as a function of time. Hold on a second. Did we make a mistake? No, I think it's correct. Okay, so write equations for the displacement as a function of time of Throckey's end of the clothesline at a point 3 meters from that end. So this point on the clothesline here was said to be x equal to 0. So to solve for part C, all we have to do is to find the equation of y of 0 comma t. So that's going to be 0.075. I'm not going to write the units again. Meters, I'll write that unit. Multiplied by the cosine of, if x is equal to 0, this just becomes negative 4 pi t. But the cosine of a negative is just a cosine, so we can also write this as 0.075 meters times the cosine of 4 pi times t. So that'd be one way to write it. This is the displacement of the end that Throckmorton's holding over here. And it also wants us to write the equation at a point 3 meters from that end. Okay, so that's going to be y of 3 meters comma t. So this is going to be 0.075 meters, and we're just going to plug in the cosine of pi over 3 times x. So I guess I won't skip steps. So pi over 3 times 3 minus 4 pi t. I'm not writing units just to keep things quick, but you should always write the units here. So this one is going to be 0.075 meters cosine of pi minus 4 pi t. And that's really all we can do, right? I mean, we could factor a pi out, but that's all we can really do, right? Oh, wait. There is something we can do. Because there's an identity for this, right? Cosine of pi minus theta is equal to what? Does anyone know what this one is? Suppose you didn't know. How could you figure it out? What if we use the what is it called? Like the addition of cosine angles? You know what I'm talking about? Like this one? Right here. Where's it? Cosine of a, that's what we want to do, a minus b, right? Cosine of alpha minus beta is cosine plus sine sine. So this is equal to cos pi cos theta minus, was it minus or plus? It was plus, right? It's plus. Sine pi sine theta. What's cosine of pi equal to? -1. What's sine of pi equal to? 0. So that whole thing is 0. So we just get -1 times cos theta. So cos of pi minus theta is equal to the negative of the cosine of theta. So we can use that relationship there to rewrite y of 3 meters comma t is equal to, what was the wavelength again? Something to keep in mind, by the way. The wavelength was 6, right? So we're looking at a position, 3 meters, that is 1/2 of the wavelength away. And what we're saying is that the function for that one is going to be negative of the function for the point y equal to 0. So we get cosine of just -4 pi t. But as said before, the cosine of a negative is just the same thing. So you can get rid of the negative sign. It's almost like it was a square or something like that. So this becomes cosine of 4 pi t. And this, I think the point of this is just to show you that if you look at a point at y equal to 0, like this point here, right? That was our final answer, right? Yeah. And you compare that to a point that is, this is lambda over 2, right? We plugged in lambda over 2, we got a function that was exactly the negative of it. If we plugged in if we plugged in x equal to 6, right? If we plugged in x equal to 6 right here, this would have been a 6. We would have gotten 2 pi, right? And then that, cosine of 2 pi minus this, is the same thing as the cosine of just, we would have gotten the same answer, right? So this would also be equal to y of 1 lambda comma t. It's the same thing, right? So this is just a way to kind of show you that this wave function, this traveling wave function, does actually produce this kind of repetitive thing that we need to have in order to have what we want. So the next thing I want to do is to talk about the wave equation. Does anyone have any questions about this problem? Okay, so let's talk about what's called the wave equation. Probably the last thing we do today. So what we want to look at now are the velocity and the acceleration of our wave. If I know that I have a wave that has a profile that is y as a function of x and t is a kx minus... Why is that not working today? Is that because of something? No. Okay, now it's working. So a times the cosine of kx minus omega t. By the way, I want to emphasize that this particular function can be generalized by putting a phase constant in here too. I'm just going to throw that in here for now. This, the way that I had it written a second ago, this only describes a function that looks like this, that starts at t equal to 0 like this. But if it was shifted in some way, you can put a phase constant in here to make it shift over, is all I'm saying. Something to keep in mind. Okay, what would the velocity of this function be, vy of x and t? If I know the position as a function of time, I can find velocity by taking the derivative, right? And in this case, this has to be what we call a partial derivative. I don't think we've discussed this in this class. Have we? Have we talked about partial derivatives in this class? I'm sure we haven't, right? Do I need to briefly talk about what they are? So suppose that I have a function that is like this. So f of x comma y comma z. And let's say that it's 6z squared plus 5xy plus, that's enough. Let's just do two terms. Say I have a function like this, okay? And I ask, what's the derivative of that function? Well, if I have a function like this, f of x is equal to sine of x, if I say take the derivative of this, you know that means take this, right? Take the df dx, and that's equal to it's equal to cosine x, right? Okay. When I say take the derivative of this, you know f prime is equal to df dx because there's only one variable. What else could it be? What other variable could come down here, right? But what if you have a function that has multiple variables? Then what you have to do is you have to specify which derivative you want to take, and the way you do that is through what's called a partial derivative. So let's say that I want to take the derivative of this function with respect to x, okay? We use these kind of curly d's to distinguish between the cap, like this d, of the kind of regular derivative. And what this tells us to do is to differentiate the function only with respect to the variable x, and you treat all other variables as constants. So for the first term right here, you treat z as a constant when we take the x derivative. Because after all, there are no x's in this function, right? So the derivative with respect to x is going to be 0. Plus, if I take the derivative of this with respect to x, we treat the y as if it's a constant. We treat the 5 as if it's a constant because it is. And we take the derivative of the second term with respect to x. What's the derivative of x? It's just 1, right? X to the first power, the derivative of that is just 1. So del f del x here would be 5y. It's very easy to do, actually. if I want to take the partial derivative with respect to y, what I do is I treat all their variables that are not y's as if they're constants. So z we treat as a constant. This is going to be plus 5x then, because y is to the first power here. We treat 5 and x as if they are constants, so this is just 5 times x. And finally, if I want to take the derivative of this function with respect to z, the derivative is going to be the derivative of the first term, which has a z in it, would be 12 times z, right? Plus the derivative of the second term, there are no z's here, so this is just 0. This is just 12 times z. You understand? Let's make it a little different for just a second, just to kind of like clarify some things here. Suppose instead of it being 5xy, it was 5xy squared. Well, then the derivative with respect to x would now just be 5y squared, right? But the derivative here with respect to y would now be different. Now if I take the derivative with respect to y, what I'm going to get is, we'll use a different color, I guess. I bring the 2 down in front of this, so I get 2y times 5x, so I'm going to get 10xy. So that's what this would be. I do that because it looks kind of weird there that our... Yeah, okay. Does that make sense? That's partial derivatives. It's really easy. It's really easy. So, when I look at this function here, if I want to take the partial derivative with respect to t, that means I treat the k, the x, the a, and the omega all as if they're constants, right? So think about it for a second. What would the derivative of this be if the only variable you consider is the t? What would the derivative be? We're going to need to do a chain rule. All right, we have to take the derivative of the outside. What's the derivative of cosine? Negative sine, right? So the derivative of the outside of this would be negative a sine of... You leave this part inside the same. And then by the chain rule, we have to multiply by the derivative of the inside, which is going to be negative omega, because we're just taking the partial derivative with respect to t. So this first term, derivative of that, 0, right? It's just an x. Derivative of this term, negative omega. So we put an omega out here, multiply by a negative sign, and that is our velocity. This is going to be the velocity of the point, right? This point is going to be moving up and down with some velocity v, and it's going to be a function of time, okay? At certain times, like x equal to 0, t equal to 0, the velocity is going to be 0. But, yeah. So this is the vy. The wave moves up and down. Here, wait. This is super confusing. If we pick a point on the wave right here, the rate at which it moves up and down is v sub y. Now we can also find the acceleration in the y direction. To find acceleration from physics 1a, we know we take the second derivative with respect to time. I'm going a little over here, but I'm going to finish this up. It won't take that much longer for me to finish this. Maybe another 5 minutes. So this is going to be the second partial derivative of this function with respect to time. So if I take the derivative of the sine function, I get cosine. And I pull out another omega, so I'll have an omega squared. And I'm going to get another negative sign, so I'm going to have a negative a omega squared here, right? We'll stop with that for now. Check to make sure that math makes sense to you all. I may have made a mistake. Next, what we're going to do is we're going to do the partial derivatives with respect to x. So now what we're going to look at is what is del y del x. This is going to be, if I take the derivative of this with respect to x, I'm going to get negative a times k times the not cosine, but sine of kx minus omega t. If I then take the second partial of this function with respect to x, we're going to get negative, wait. No, we did it right. So the derivative of this, the cosine, gives us a negative sign. The derivative of the inside gives us a positive k, so it's a times k. If we do it one more time, the derivative of the sine function is a cosine function. And we get another k from the derivative of the inside, so a k squared. Right? Yep. Next, what we can do is we can take our two functions that we have right here and find the ratio of them. So if I take del 2y, del t2, so the second derivative with respect to time, and I divide by the second derivative with respect to x, what do we get? So the time derivative is up here, negative a omega squared cosine of kx minus omega t. We divide that by del y, the second partial with respect to x, which is this one, negative a k squared cosine of kx minus omega t. And now we get some cancellation. This one cancels with this one. The a's cancel here, and these two become positive. So we end up getting that. I'm going to write it in a slightly different way. Del 2y del t2 is equal to omega over k squared multiplied by, and I'm just going to take this piece and move it to the right-hand side, the second partial of y with respect to x. But omega over k is actually equal to the velocity. You can see that pretty quickly because omega is equal to 2 pi times the frequency, and k is equal to 2 pi divided by the wavelength. So this is equal to f times lambda, which is equal to the velocity of the wave. So now what we're going to do is we're going to say that if that is equal to v squared, normal way that this is written is to move the v squared to this side. So we have 1 over the velocity squared multiplied by the second partial of y with respect to time. This 2's in the wrong place. Sorry about that. Is equal to the second partial of y with respect to x. And this is called the, is this the one-dimensional wave equation? Yeah, it's the one-dimensional wave equation, right? It doesn't specifically say that. We just call this the wave equation. Okay, so any function y, oops. This is an extremely important equation in physics. Any function y, any function f of, no, we're using y, right? Y of x and t. Do I have enough room to write this? That is equal to some function of either kx minus omega t or some function of, this is going to go off the screen, x minus vt will satisfy this equation and will represent a traveling wave. Represent a traveling wave. Okay, so this is a really important equation in physics because it doesn't just show up in this class. This is the first time you kind of get exposed to it, is in Physics 1b. But what shows up in this equation is you have the second partial with respect to x on one side, the second partial with respect to time on the other side, and then 1 over velocity squared shows up right here. I can say that, like, in Physics 1c, we're about to, I think this week, no, it's 2 weeks from now, I guess, we're about to show that this same equation shows up in electricity and magnetism. And this is how Maxwell figured out that that light was an electromagnetic wave. But one of the things your book does not mention is this piece right here, and this is extremely important. I don't know why your book doesn't mention this. Any function that has this form will automatically satisfy this equation. I'm way over time, so I don't know. We'll probably just start next time with me showing you that you can pick any function that has this general form right here, and it will automatically satisfy this equation, which I think is really cool. Anyway, so we'll start with that next time. I'm not convinced that we've done enough in class for you to really do your homework yet. So if you want to work on your homework, you're probably going to have to read ahead in the textbook, but reading ahead in the textbook is a really good thing. We only have 2 chapters left. It's chapter 15 and 16 in the textbook, and we'll be spending the next 3 weeks or so covering them. So highly recommend that you read ahead. Anyway, so that's all we've got for today. Hope you have a good day. We'll have our first, so there's a lab this week. I think it's H-15. Check the syllabus to make sure. And it's the first half of the class that's going to be showing up for that. And then next week we have an exam. All right, so we're going to stop there. Hope you all have a nice day. See you soon.